Lecture 2B, independent property of the pure substance. Um, so let's define a simple compressible substance before we go to the independent property of the pure substance. So a simple compressible substance would be a material that can be worked upon by a pressure forces. So if we apply pressure on it, so that means like it will there will be either change in the volume or change in the temperature in it. So yes, but we have to neglect the electrical energy, electrical, magnetic, or chemical work mode in it. While this is indeed definitely restrictive, but it is more important in a mechanical engineering application. But and also the following important statement can be provided. As for a simple compressible substance, two independent intensive thermodynamic property would be needed to define the state of the system. So that means like if I'm talking about a very simple compressible substance, so any independent property between, let's say for example, for a fluid, simple fluid, PV and T, any two independent property, if I got it, then I can find another third property. Any two independent property would be needed to define the state of the system. Now, talking about the superheated region, so all these three property like P, V, and T, they are independent on each other. So if I need to find a pressure, I can find the pressure in by using the temperature and volume. If I need to find a volume, I can find volume by having temperature and pressure. And if I need to find temperature, then I can find it by using pressure and volume. But for the two phases mixture, in our last lecture, we said like about the dependency of the pressure and temperature inside the vapor dome. In other words, the dependency of the pressure pressure. If I keep the pressure constant, then the inside the vapor dome the temperature also remain constant. Now if I increase the pressure, the temperature would be increasing. If I decrease the pressure, the temperature, saturation temperature, if you remember, would also increase. So that means like inside the vapor dome, the pressure and temperature in a two phases mixture, the pressure and temperature are not independent, they are depending on each other. So definitely we would need another property so we can define the state of the system. So if I'm saying PV and T actually, so these two are dependent on each other. So if they are dependent on each other, they would be considered as one property. So if I would need to find out the volume, so I can only find out the volume. I cannot find the volume using the pressure because the temperature is also related to it. So I would need another property. And if you remember in the last lecture, that property was, and that property can be called as the quality. So now if I say like if I need to find out the volume, I can find the volume using temperature or pressure, and also another independent property which is actually the quality. So why we need it? Definitely over here we need to describe many different ways to capture the relationship between the two independent property and the third dependent property for a simple compressible substance. The first term, and then obviously we need to derive a thermal equation of the state. The thermal equation of the state would relate these different simple properties. Like for example, if I'm talking about the pressure, then that pressure can be found out as a function of two independent variable, temperature and volume. So that's why I need these property to fully define the state of the system, or I need to define the thermal equation of the state. Definitely, if I'm looking at the not the simple substance, the formula would be, or the equation would be getting complex, and more variables will be involved. The first thermal equation of the state, which actually was is, or if I'm saying the earliest thermal equation of the state which was actually derived, was the ideal gas law, or the ideal gas equation. For many gases, that is specifically at low density and far from the critical point, it is right. It is definitely possible to write a simple thermal equation of the state, which accurately describes the relationship between pressure, volume, and temperature. These equations were developed in earlier 1600 and 1800. Based on that one, if and obviously, and then later on modified with the Avogadro number, Avogadro law. So based on that one, the equation of the state is the combination of Boyle's law, the Charles law, and the Avogadro law, and that is PV is equal to nRT. Now, if you can check the below graph or the graph shown, this graph is exactly the Boyle's experimental law and the plot of the Boyle data. It is the data between the 1 over p and actually and the volume. You can check that the pressure and volume by Boyle's actually say like the pressure and volume are directly proportional to each other. So directly proportion mean like P is proportional to 1 over V. So that means like they have got a direct relationship. The ideal gas law was first stated in a form of roughly equivalent to the above equation by Clapeyron. This the whole equation was actually done by the Clapeyron. Uh, and obviously many other thing. Avogadro number is there, universal gas constant is there. The above law is actually based on PV is equal to nRT, where R is actually in terms of universal gas constant. If I'm just writing the n over here, so that means like p would be is equal to RT. Actually the bar show that it is actually volume per unit mole, and the R is actually whatever the unit is, that would be per kilomole actually. So PV is equal to RT. That is actually in specific term, but that's specific in terms of moles. Now if I need to have specific in terms of mass, that is specific for the specific gases actually, so that means I would be dividing with the mass, the and obviously n by m is actually 1 over m now. So moving forward, that would be equal to PV is equal to RT. That means like this volume is now the specific volume in terms of mass, and that R is also in terms of kg. Now that R is actually specific R. That means like for the oxygen it will be different, for the nitrogen it will be different, and for other gases it will be different. So what does this say like? It is actually telling us R is definitely a constant now. So definitely this law or this equation is deriving a relationship between pressure, volume, and temperature. So that if in a simplest form, PV by T is equal to R. That means like PV by T is equal to constant. So if I'm moving from one state to another state for a simple gas, so that means like I would moving in this equation, P1 V1 is equal to P1 V1 by T1 would be equal to P2 V2 by T2. So that equation would hold from state 1 to state 2, as that means like the R was constant. So that means like PV by T is equal to constant. Now if I'm moving in an isochoric process, which means a constant volume process, so the relationship would be P1 by T1 would be equal to P2 by T2. If I'm moving in terms of constant pressure, so that means like it will be V1 by T1 would be equal to V2 by T2. And if I'm moving in terms of constant temperature, so that means like P1 V1 would be equal to P2 V2. So that case, that means like this law is just telling us a simple relationship between pressure, volume, and temperature, and the relationship when I'm moving from one state to another state. I hope you understand this lecture. I hope you understand the concept of independent property of independent variables, the independent property of the pure substance. If you have got any question in this lecture, you can post it on the Google Classroom, and definitely I would be able to answer that one. Thank you very much. Have a nice time.